In this video, I'd like to do some at least one probabilities and a couple conditional probabilities. We'll be using this summary of a set of calculators ACC keeps on hand to loan to students. Here in number one, we're asked to find the probability that when three different calculators are selected, that at least one is damaged. Well, the three different part's important. It means I'm making three selections without replacement. That's the only way I can guarantee getting different calculators. And since this is phrased as an at least one, I'm going to remember that the probability of an at least one is always 1 minus the probability of none. So I'm going to start by finding the probability that none are damaged on those three draws. All right, well, I need a way to summarize that. So when I look at this table, I see that the non-damaged calculators are the ones that are either good or okay. So those are the calculators that I would be selecting if none of them were going to be damaged. So I'll just write not damaged or summarize that with an ND. So I want to select a calculator that's not damaged, and then another one that's not damaged, and then another one that's not damaged. Well, this is a multiplication rule problem with all of those ands in there. I'm doing something on a first trial and then another thing on a second. So let's just go through this. I need to know how many total calculators there are. And I don't remember from our previous video, so I'm just going to add these values up. And there are 78 total calculators, so 78 calculators. So the first time through, there's 78 calculators to choose from. And these are the ones that are not damaged, so I need to know just that amount. Now, I could look here and say there are 11 over here, so I don't actually need to do any subtraction. I can just say that there's 67 of them, but if you wanted to, you could confirm that by adding the values in the orange box here. All right, well, next time through, I'm going to get a different calculator because I'm doing this without replacement, so that calculator's gone. So there's 77 left, and I'm assuming I've already gotten one that was not damaged, so there are only 66 of those left. Times, and I have 76 calculators now, because now I'm assuming I've already drawn two, and only 65 of them would be not damaged. So let's find this probability. 67 out of 78 times 66 out of 77 times 65 out of 76. And I find out that I get a 0.6, and when I go to round to three decimal places, that actually pops that up to a 630. But now we have to recall that's not what we were trying to find. We were trying to find the probability of at least one damaged in three draws. And that's 1 minus the probability we found for none. So let's see, 1 minus 0.630 is going to be 0.370. Just thinking about doing that subtraction. All right, so there is our probability to three decimal places. Always thinking of an at least one as 1 minus the probability of none. Number two gives me a similar problem, but this time I'm selecting with replacement. What is the probability that when 5 calculators are selected with replacement, at least one is damaged? So in a lot of ways, I'm still thinking in the same terms. And at least one probability is still going to be a 1 minus the probability of none. So this time I'm thinking about the probability of getting 5 non-damaged calculators in a row. It's still a multiplication rule problem, and I could write it out like this one where I go not damaged and not damaged and not damaged, and then two more of those. But I'm just going to summarize it here and know that this is a multiplication rule problem because I'm selecting a not damaged calculator and then a not damaged calculator and so on. But this time, the first time through, well, there's 78 calculators to choose from, and 67 of them are still not damaged. So I reach in, I grab a calculator, I look at it, and see that it's not damaged, and then I put it back in and mix everything up again. So the next time through, I'd have the same probability. So I'd multiply this number to itself 5 times. All right, so let's find that probability. 67 out of 78 to the 5th. Making sure to use those parentheses if you want to do this in one step. If we want to do it in 2 steps, I'd go 67 out of 78 to the 5th. Get that same probability. All right, but now I need to remember that's not what I was actually searching for. This probability of at least 1. Damaged in 5 draws with replacement is 1 minus that value. So 1 minus 0.468 is going to give me a 0.532. All right, so those are our 2 at least 1 examples. One done without replacement, one done with replacement. These are very nice when we get to do the with replacement, or at least assume they're independent events, because I get to use exponents and I don't have to multiply different fractions out. But we do have to be careful to make sure we understand when those things occur. Problems 3 and 4 involve conditional probabilities. Number 3, what is the probability that when a calculator is selected, it is damaged? So probability of damaged, given that it was a TI-83. These conditional probabilities are always special. I always just assume the thing after given has already occurred. So when I'm told that given it was a TI-83, all of a sudden in this problem, the only calculators that exist are the TI-83s. The thing that follows the word given limits my sample space. I know I am going to get a TI-83. It is guaranteed. So the calculator I'm selecting is among these 24, 34, 36 calculators. And how many of those are damaged? Only 2 of them. Well, that's a 1 in 18 probability, or about 0.056. Actually a 5 repeating, but rounding to 3 decimal places, 0.056. Well, with these conditional probabilities, that's the big deal. We read the problem and the thing after the word given is guaranteed to occur. What is the probability that when a calculator is selected, it is a TI-83 given it was damaged? So I'm looking for the probability of getting an 83, and what I know has happened is I'm selecting a damaged calculator. Given that it was damaged, I'm guaranteed a damaged calculator, so I'm only selecting from these calculators. So there are only 11 of those. And how many of them are TI-83s? Well, so I'm selecting from the damaged one, only 2 of them are TI-83s. So 2 out of 11 is about 0.182. Well, that's the last problem I have printed here, but you know what? I feel like doing one more conditional probability problem. So, let's just make one up. What's the probability of getting an OK calculator given it was a TI-36? Well, before we solve this, I'd like you to take a moment, pause the video, and write a question in words where this probability statement would be the answer. Just like this question we wrote down in probability statement. Write down the question that would match this. Pause the video here and try that. What I'm hoping you wrote is something like this. What is the probability of selecting an OK calculator given it is a TI-36? And again, what we're going to think about is the thing that follows the word given is a guarantee, right? That is going to happen. So the only calculators I'm selecting from this time are the TI-36s, of which it looks like there are 21, and only 10 of them are okay. Well, that's a probability pretty close to just 0.5. 10 out of 21. 0.476, just under 50%. Well, those are the questions I wanted to go through in this video. There are a few videos below this one posted about the counting rules.